Hi everyone. In this video, we're going to be working through two problems. The first is number 18 in section 1.1 of the text. We're asked to compute R4, the right endpoint approximation for the function x squared minus 2x plus 1 on the closed interval 0, 2. So the first thing we should do is compute delta x. So delta x is b minus a over n. In this case, that would just be 2 minus 0 over 4, which is just 1/2. So using this, we can find our endpoints for our intervals. So our intervals, so we're starting at the leftmost portion of our initial given interval. So that would be 0, and we're going a half away from 0, so that would be 1/2. Our next would be starting at 1/2 and going to 1, so we're just adding another half to make sure that these intervals all have length 1/2. And we continue in this way. Perfect. So now we write out what R4 is. So that would just be sigma I equals 1 to 4. Now, since we're using the right method, it's f of xi delta x. If we were using the left endpoint method, L4, we would be computing f of xi minus 1. But in this case, we're using f of xi, so that's equal to, we start with f of 1/2, because that's the right endpoint, times delta x, which is 1/2, plus f of 1, the right endpoint of the second interval, times 1/2, plus, and we go up to f of 2 times 1/2. So this ends up being 1/2 squared minus 2 times 1/2 plus 1 times 1/2 plus f of 1 is 1 squared minus 2 times 1 plus 1 times 1/2 plus f of 3/2, which would be 3/2 squared minus 2 times 3/2 plus 1 times 1/2. And finally, 2 squared minus 2 times 2 plus 1 times 1/2. And after doing some simplification, this works out to 3 over 4. Now this approach is purely algebraic. If we wanted a more geometric approach, here is the graph of the function. I used Desmos to get this picture. And we know that our intervals are 0 to 1/2. So we draw our partition, and then 1/2 to 1, 1 to 3/2, and 3/2 to 2. And we can't forget about our vertical line at 0, the beginning of our interval. Okay, so since we're using the right endpoint method, we draw our rectangles starting at the right, like so. And then we compute the areas of each of these rectangles. Well, the first one has height 1/4, and they all have width 1/2. So we have 1/4 times 1/2 is the area of the first rectangle. The second rectangle has height 0, so the area of that is going to be 0. The third rectangle has the same height as the first, which is 1/4, so the area is going to be 1/4 times 1/2, plus the area of the last rectangle. So that height is going to be 1, and we're just multiplying that by 1/2 because that is the width. And after doing some simplification, this sum ends up also being 3/4. Thank goodness. So moving on, I want to talk about question 53 in section 1.1, which is a more conceptual question. So if we have a function on the interval AB such that f of a is greater than or equal to 0, so I'll put f of a here, and f is increasing on this interval. So increasing just means it's always going up and never dips down. So let's try to draw something that's increasing like that. So we need to explain why the left endpoint estimate is a lower bound for the area below the graph. So what is a lower bound? Well, essentially what that's saying is that the left endpoint method gives the smallest possible approximation for the area under this curve. So let's partition AB like we usually do, like so, and we'll pretend those are equally spaced. So in order to make the areas of these rectangles as small as possible, since each rectangle has the exact same width, the only thing that we can change is the height of the rectangle. So let's look at this rectangle here. We want it to have the smallest height. So if we use the left endpoint method, that means our height is going to be this. Now, let's say we pick any other point in this interval. Well, then that point is going to be higher up than our left endpoint of the interval. And that's because this function f is always going up. It's increasing. So if we pick, for instance, this second yellow point, the height of our rectangle would be a little bit bigger than if we used the left endpoint of the interval. And that, in turn, means that the area of that rectangle would be larger than the area of the rectangle using the left endpoint. So this isn't just true for this one rectangle, it's true for all of these rectangles because the function is increasing. So that's why the left endpoint method, in this case, when the function's increasing and f of a is bigger than or equal to 0, gives a lower bound for the estimate of the area below the curve. Thank you for watching.